Okay, so today is the last lecture of Professor Isabella. I remember you that we have, she's the president of the Catalan Society for Statistics, and she's very busy, so we are lucky to have her here. And we are waiting for some material. Isabel?
Yes, I know, really.
Okay. You will send them.
Okay. When I finish, I am going to send you everything because
Okay.
I
Yes.
don't have enough time, you know.
Okay, so please start whenever we're here.
Sorry, 1 minute.
You want me to pause? Ready to go?
Yeah. Okay. Sí. Sorry, because I forget to put my computer. Okay, everything is okay. I am going to start where we finished the last day. In fact, I have the same session in it. Then 1 minute. Okay, you remember the example that I was showing? I want to continue with the same, in the same point. You remember, because the last that I was explaining is this very important point around to sum square of the error. You remember when we try to do some models? In fact, regression or neural network, doesn't matter. The main idea is when you want to measure the uncertainty of the response, and this is the main focus where statistical analysis is very important, because you can see, remember the example where we was trying to, the example you remember in this part, when we was trying to some model, you remember that the response, Y, was altura, and X, the information. In this case, only one variable, only one column corresponding to peso. You remember the data? Then in this case, you can see a very easy example where the result of the modeling, in this case with LM, remember with LM, I try to model the response by a linear regression. Then only two coefficients are needed to do that, intercept and slope of the line. In this case, you can see where this R square is measured based on the percentage or proportion of the variance that it's explained. No, you remember I was explaining that if you, for instance, use ANOVA, this function of R, you can see the contribution of the response, the contribution in response that you obtain when you use the information X is this one, and residual is the part of the variability of the response that you cannot explain with this information X. And in this case, is close at 50%, but 50% is explaining. No? And then this main idea you can see in linear regression, there are several procedures, typical procedures that you can do. For instance, an F-test. F-test is basically to compare variance, and the result of this F-test detect that is significant the information that you consider, because 50% is enough in order to say you are really explaining something of the variability of the response. Then this is a main part, maybe from a statistic, the use of test analysis in order to check the quality of the test. Then in linear regression or in statistics is useful, and everybody know that it's necessary to do this type of test. However, when you try to use machine learning in general, machine learning procedures, mainly based into model through neural network, for instance, you need to remember this part. It's necessary to check this part of the modeling, because really is the part such that is going to do some performance assessment of the quality of your model. Okay, then the idea is the statistics in machine learning. The main role is to recover all the results related into contrast and certainty measures in this new scope, if you want, related with more complex modeling. Okay, then I come back to some slides that I was showing the last day. I sent, you remember? I need to change again the screen. A moment. I remember it's better if I put full screen, you remember? Then let me to show with more details neural network, okay? Oh, sorry. Okay. Now my intention is to talk with more detail with neural network in order to introduce this main point from statistics. Neural network. Okay, the idea of neural network, I was introduced last day. Input is some information, for instance, in my example, X, and output is a response. For instance, in my example, Y, no? Then linear combinations in here, in this step where you try to generate an output, linear regression is a typical one in a statistic, is the one. And the idea is to convert this black box in some more complex models, such that can really fit a strange or complex outputs, no? The proposal of neural network is based on to consider some layers and with neurons, based on this structure, if you want. Remember, I was showing this picture. This one corresponds, each neuron in input layer correspond to each variable in your dataset, if you want, each column, okay? The more simplified version. You remember the first day I was explaining that the information, in general, information can be a more complex object, for instance, an image or time series, etc. And in every case of that, you need to do some embedded in Rn. And in this case, this initial structure of some columns or variables is that you need in order to start to do the more easy version of neural network, okay? Then in this part, you can see each neuron corresponds to some variable, for instance, peso in our case, but in general, we say features. We prefer to use the word features because in general, these variables, this neuron corresponding to one dimension of this Rn space where you embedded your information, maybe is not interpretable. Then many times a neuron really is only some features, some characteristic of the information that you need to export in here. But remark that it's needed that in new data, you can detect these new features, okay? When you consider these neurons, then the idea is to fix output. Output layers, you need to take some attention because output, if you think in the example where the output Y is altura, you remember, you only need one neuron because the output really is a function. For instance, in the case of linear regression, you are going to do some combination, linear combination of input layers to one output layer with only one neuron, the response, with only one formula. But in general, a neural network has to consider several neurons because many times the response is categoric. Then in the case is categoric, that you are going to model is the probability for each category. Then, if, for instance, if your response is something like 0, 1, then you need two neurons, and the response of the neural network is the probability of 0 and the probability of 1 under the input version. Okay, the idea is also your model are going to consider two fixed. For instance, in the general case, you are going to compute the expected value of the response when some information is fixed. When some information is fixed, you have a deterministic expression, and you can compute a deterministic value corresponding to the prediction of this one. In the case of continuous variable, only one. In the case of some different values for the response, for each one, you are going to obtain a probability for each one, okay? Really, the neural networks in general are going to compute some different values, and then you only need to balance using that everyone plus this one plus this one plus this one has to be one. No? Okay, really this is the expression, okay? This is the expression of the easy neural network, but it's important to remark this case because it's very easy and you can understand the recursive version, okay? You can see the response. This is a model corresponding, for instance, in linear regression, I put response alpha plus beta x. This is the model of linear regression. With neural network, you can see response is alpha plus linear combination of some weighted, some coefficients multiplying a nonlinear transformation of a linear combination of the information. Okay, let me to show with the picture. You can see the previous image.
Isabel, can you speak a little bit louder because the voice became...
Yes.
Yes, thank you.
Let me know if it is correct now, okay? You can see, look at the picture. You can see the picture. You suppose that this one is x1, x2, x3, and then each row corresponds to represent a weight. Then the idea is each number in here is combined linear combination plus independent term and obtain this one, a new value. But before to take a value, you are going to do a nonlinear transformation. This nonlinear transformation is the activation function. The activation function, you can see, activation function. And in general, you can take as a logistic function. A typical activation function is logistic function. I can give you some additional comments on that. But for now, in your mean, activation function, take a linear combination and transform using logistic function. And the main goal of this activation function is to focus some linear combination of the information in a small point in a local term. And you repeat for each neuron in some hidden layer. You decide how many hidden layers do you want, and you have to decide how many neurons in each one. Okay? The architecture of a neural network is fixed, input layer and output layer, but you can decide how many hidden layers and how many neurons in each one. And moreover, you can decide if the connections is only in this sense, sequentially, or you want to combine linear combination, for instance, adding some rows from here to here. But the most easy one, in order to understand the complexity of a neural network, is this one. Then you can see if the activation function disappears and input layer disappears. This one is the linear regression, the typical linear regression. Okay, when you see this model, you can see in a very, very easy case, which few neurons in the input layer and few neurons in here and few neurons. At the end, you need a lot of coefficients because when you want to fit a linear regression, you only need to fit A and B or alpha and beta, two coefficients, no? That you see. But when you are working in a neural network, you need to fit the weight for each row. No? And then you can see there are many, many parameters that you need to fit. This is the main problem in a neural network, and this is the main goal in machine learning techniques, because you need to optimize very strong problems, because there are several variables or something, weights that you need to fit. In this case, you can see this is expression, then you need to fit this one for each k. For instance, if the response is continuous, k is equal to 1, then 1 in here. But for each neuron in a hidden layer, you need to compute 1 weight in here, and moreover, a lot of weights for all these arrows. Okay? Then the most important is to understand this is for me, the most important to understand that the expression of the term for modeling, you can write, and maybe it's more complex than a linear relation, but in fact, you have several weights or several parameters that you need to fit. Okay, but when you try to do it, really, let me to show directly, let me to summarize maybe the main points. But when you try to do this one, the main problem is this one. The global minimum is not guaranteed. When you fix some error to measure the procedure, in this case, in neural network, in the example, for instance, mean square error, like in linear regression, global minimum is not guaranteed. Then it's easy to get some very, very bad result. No? One technique, maybe the most typical one technique to converge the procedure is to consider some penalization. Then you try to fit this one, you try to search some parameters. No, remember the parameters, the weightage you need to put in here, a lot of weightage that you need to fit in order to obtain some modeling. And when you try to measure the error, you need to compute to minimize this function. Then the most typical way to search a good local minimum is to add some penalty in here. There are several proposals. For instance, in Ripley, you can see several ones, very classic results, where you can fit this parameter in this interval for continuous response and in this interval for non-continuous response. And you can see the idea is this one is a penalization when you have some weight too much large. No? It's the main idea. This is typical example. This is a typical strategy that you can see in several optimization problems, not only in this one. Okay, that is some example in order to understand that all techniques that you know from optimization problems, you can adapt in this case. Let me show an example. I was explaining let's say, for instance, ozone, no? This data set, you remember data set ozone, where you have several variables that you can consider. And in order to do some more didactic example, we are going to consider only temperature, pH, and EBT. Then if you are considering to use air, the function is nnet. The function is nnet from library nnet. Remark that is a very didactic package. Exists a lot of ones for to do it, but it's very easy to use and very easy in order to read the response and etc. In this case, you can see ozone. Remember the formula is the same that in linear regression. Only change that I say to air that I want to do a neural network. Then in this case, I say size 2 is because I am going to put only 2 neurons in the hidden layer. Okay. Then 3 neurons in input layer, 2 neurons in hidden layer, only 1 hidden layer, and 1 neuron in the response. 1 neuron in the response because my response is continuous. Then I only need one neuron. And in order that neural network know that, I put lean out true. Lean out true is because I say I am going to consider the response continuous. Then with this one, I say only 1 neuron in output layer, 3 neurons in input layer, and 2 neurons in hidden layer. When execute the modeling, the result you can see in here. If you do, in this case, for instance, the model is called ozone.net, and the summary, remember summary is like the same. It's exactly that I was doing with linear model. But now, when I say summary, the response that I am going to show is the coefficients, the weightage. For instance, in this case, B corresponds to the intercept parameter. H1 is the first neuron in hidden layer. This letter I corresponds input. O, for instance, in here, O is output. Then, if I want to know which is the weight in the arrow from the second input to the first hidden. No, for instance, second input corresponds to the second variable, EVH. Then the coefficient with EVH such that go to the first neuron in the hidden layer is 0.97. I need to see. Then in here you can see exactly which is the coefficient, and you can imagine that when I repeat the fit, if I repeat the fit, the numbers are going to change maybe because it's a optimization problem, and in this case converts, but it's not clear that converts to the global minimum. In fact, you can check and you are going to see.
Isabel, and when is negative, means that
negative in here?
Yes.
Is a coefficient. The coefficient is like in linear regression, maybe positive or negative is a weight.
So it's less probable.
Is really, you can see in the definition, weights are real. Can be positive, negative, bigger than 1, it doesn't matter. Really, only a real coefficient. If you want, if you are trying to interpret the coefficient of the value,
yes,
is not you cannot do it in general with neural network. It's not possible. No.
Okay.
Because you can see that this is the information is a contribution in the first. In this one is in the first neuron in hidden layer. If you have several neurons, maybe each one of them are going to capture some information that in sometimes maybe you try to understand which is the configuration of the information in this hidden layer. But in general, hidden layer are going to perform some mix of the information, reducing the dimension, but you cannot really recover which is the structure of the pattern.
Okay. Okay, thanks.
Remember that I was showing that total sum square, no? You remember that total sum square is very, very important. Correspond. Is a question? I cannot. Can you repeat the question? I lost. I see. Sorry. I see the chat. Okay, some questions. Are double B angular coefficient of the linearization? No. There are some cases where you consider a neural network with some complex structure when you can fix some properties on the weight. But in the example that I show, it's without constraints. Then all results are considered. I lost. Okay. Okay, then total sum square, remember, is this measure that I have to put in my mean when I have a response that I want to fit. And remember, the most easy model when I want to fit or I want to estimate the expectation of some response is the mean. And then is my value of the reference, is a total sum square. Of course, if you divide this one for n, for the dimension, you are going to obtain the variance of the response, okay? In the case of linear modeling, with this one, you remember that we can obtain some strong reduction of the residual sum square, because at the end, when I do a linear regression, in this case, I obtain that the prediction of the modeling led to simplified information, and only from 1,000, I obtain that only 7,000 is not explained. Okay, really, linear regression led to explain a very strong part. In fact, can explain a 65% of the variability. However, in this case, neural network cannot explain nothing. You remember that in this example, neural network is not explaining. We are not put, you can see in this example, without constraints, I am not considering nothing. Then now let me show the main idea, because this is strange maybe for you, because neural network potentially is better than a linear regression, but you have to put in your mind that if you consider a neural network and you consider some random architecture, you are not going to obtain good results. Sure, you really need to work with a neural network, searching a good structure and several steps. Then I am going to show you the main 2 steps that you have to do in order to fit a neural network. Okay? The main one is this one. I am not sure which is the global minimum. I don't know if this exists. Then there are several strategies. The most easy one is this one. This is the most easy, but you can see it's a heuristic, very simplified version. But the most important is you understand that you can consider different strategies from numerical point of view. This one is I am going to repeat. No, I can do a for. Let me to show this syntaxing. You can see for. For is for like all language is equal. In R you have to put for A in 1, 2, 7, 100, sorry. Then in this case, I am going to say, I am going to do this one between this one and this one 100 times. Then I am going to repeat a neural network. You can see, I repeat the fit. It's exactly the same. I am going to repeat the fit, looking for to reduce the residual sum square.
So Isabel, so this depends on the initial guess. Would depend on the initial guess, the output?
Yes, of course.
You're sampling the initial guess more randomly, and you're repeating many times to have an average response?
Yeah, exactly. In this case, I only show, because you can see, I am not considering any strategy in order to check the best initial point. I only want to show that if I repeat 100 times, I am going to get a very strong reduce of the residual sum square. The idea is you can improve yourself, know several techniques for to do it, and you can apply. But you can see with some very easy way, only repeat without no constraint, without controlling shifts. You are getting a strong reduction. You can see that now R square. You can see this is a residual sum square is 70%. Then now with 100 runs, you get almost 1 time to improve the determination coefficient R square to 70. Remember that 65 was linear regression, okay? This is the first idea. The idea is to understand that global minimum is very difficult to search, then different strategies. One of them, for instance, is one, because it's easy, and from the didactical point of view, I think it's enough. And another one, maybe you can see in this 100 runs, this is the residual sum square. You can see sometimes it's reduced, and this is the winner, no? When you really reduce more than linear regression. Another strategy is this one that I was commenting, that you can consider some penalize in the data, no? If you consider some lambda in order to fix some more slow increase in the coefficient, that you can improve. Then, for instance, this one. This is a typical. In this case, you can see lambda is. I passed some quickly. Sorry. In this case, no lambda. Lambda is going to correct this one. Sorry. This is a very important check when you do a neural network, because you can see this is a response, and this is one of the covariates. Then this type of plots are very necessary. If I am working with a linear modeling, for me it's clear that I have to do. When you are working in neural network, not many times the people is doing this type of checks, and really are very important, because you can see you are considering modeling of the response based on 3 variates. Then for each one of them, it's important to look for a more regular pattern. Then, for instance, in this case, you can see it's not continuous, or suggest that of course, the neural network is a continuous model. However, that you can see you have a very, is continuous and of course irregular and etc. But in practice, this pattern maybe not correspond to the regular pattern in your mean that you are thinking that you have to obtain. Compared with linear regression, because in linear regression, each covariate, when I fix, the idea is, you can see in here the instruction. The idea is to fix for the other variables. In this case, is temperature. Then EBT and EBH is fixed with the mean pattern. Then you fix the mean pattern for every one of them, and one of the variables led to move in the rank, and you can see which is the model, that you are fitting with these values. Then when you look for this, when you are detecting something like this, it's not very good because not too much close of your idea of regular. And you can compare, for instance, you are working in, for instance, in this case, ozone and temperature. You are thinking that the influence of temperature is more close to some physical relation. Then this kind of patterns are not too much according to the intuition from physical point of view. This is the check that you can do for every one of them. And in this case, this is that I was showing, but you can check for each one. Then we have 3 variables, then you can check the relation. Of course, in linear regression, in typical linear regression, I can see lines. The idea of neural network is to improve the line with some regular pattern, but non-regular in our case, no? Then that I was introducing this idea of decay. You can see this parameter, decay, correspond to the lambda in the formula that I was showing, that you can introduce in net formula. And at the end, you preserve close the performance with 70%. But now, regular pattern are obtained. Maybe in this case, you are not getting, maybe you can check different parameters for lambda in order to improve this one. But for us, this one is a good result, okay? Or enough from.
So you restrict the interval to get only to the continuous case? You adjust?
In this case?
Yeah.
For each one?
Yes.
Yes, the idea is to fix the interval corresponding to the observation. If you observe this EVH between this interval, you fix the same one between the minimum and maximum in the data set.
Okay.
Then you do each point is because you consider grid equally spaced. Okay. To fix between the minimum and maximum that you observe for each one. Grid, you select a grid and fit with the formula of neural network. Okay, these pictures are without data. It's based on the model. When you have the model, you have some parameters, you have a formula, and you can check. No, the formula is a formula. Okay, let me do it again. Oh, sorry. Because you have a formula. Then when you fit these numbers, alpha, weights, and etc., you can put and given some x, and the idea is to fix x1, for instance, with a mean x2, with a mean of x2, etc. And some of them, oh, sorry. It's very sensitive. And is, for instance, if I want to check x3, then I move x3 in a grid between minimum and maximum that I observe in x3, and the other ones fixed with a mean pattern. And then I can check this formula, which is a behavior from an analytical point of view, okay, without data. Then at the end, for me, this model can be, you can continue, and you can continue and remember, very important that I was telling some meta parameters, because parameters are typically, for instance, a weight, alpha, beta in a linear regression, but in machine learning are very, very important the meta parameters corresponding to decide how many hidden layers, how many neurons in each hidden layer, which is the decay parameter that you want to fix. The decay parameters in order, decay is because you know is in order to get some regular procedure in gradient descent, because it's a main technique for to fit this this type of techniques. But there are several parameters that we say meta parameters because you need to fix previously when you start to doing the fitting. There are several techniques to fix the meta parameters, but the most typical one is to consider a grid. Okay, a strong grid for instance, for the case, several parameters for the different hidden layers. For instance, to say, I am going to consider one hidden layer, 2 or 3. And for each one, I am going to consider 2 neurons, 10 neurons, 20 neurons. And you do a grid of different characteristics, fit the model for each one, and decide which is the best architecture that you have to consider. Then you fix the meta parameters. You can see this procedure is introduce some noise from scientific method because you use the information several times. And this is one of the main reasons because we need to use some techniques of validation of the method based on cross-validation. I don't know if you know cross-validation, but the most easy. I don't know if you was working on cross-validation, but the most easy example is to separate the data set into types. Internal validation and external validation. Then, for instance, you consider if you have a large data set, you can consider some part in order to do some part of the analysis and another part of the data to do another part of the analysis. Really, you need to separate in a lot of types if you want to do very, very strict in the procedure. But many times, depending on the capabilities, because depending on the dimension of your data set, you can do one technique or another one. And really to talk on external validation and moreover on cross-validation, we can be a lot of hours because there are a lot of different works when propose different techniques for improve this procedure. Let me to show an easy example where we are doing we decide to divide the data into sets. This is the most easy, okay? The cross-validation. You consider training and test. And that we want is to take a sample of the numbers for decide which rows of data set are going to live in training and which rows of data set are going to live in test. Then now, not only one data set, I have two data sets. One of them training that I am going to use for fitting the model and test that I am going to use to compute R-square. Because in the procedure, you can see from a statistical point of view, you have two steps. One of them is fit the parameters, and the other one is to compute the error. Then 2 steps from a statistical point of view, 2 sets. In fact, if you think I need to decide meta parameters, then really I need to consider more divisions of the data set. One of them for decide the meta parameters, another one for training, another one for testing. And moreover, really you can do very complex procedures for fitting. And I have to remark that in R exists some library like tidyverse. I don't know if you know. Tidyverse led to do some strong cross-validation procedures. But in Python, of course, exist several ones too. In this case, let me to show the results with training and test, because it's very interesting that neural network, with this improved neural network, where I do 100 times and consider penalization and scale the data, a lot of things. At the end, the residual sum square, sorry, the total sum square, you remember, the R square is 73%. Okay, then maybe you are thinking it's very good, but when you check the same model comparing Remember, always the same. Total sum square is the same value as the reference. When I consider residual sum square, but you are computing in new data from test, this data that you are not considering for training, then the square change, and in this case, decay as 50%. That at the end, in this case, in this example, with internal external validation is worse than linear regression. You can see with linear regression, the advantage is that if I consider internal external validation, the result is the same. Because internal, really, when I do linear regression, the most easy model, the parameters are computed from deterministic because I have some analytical formulation for to do it. I don't need to use optimization procedure. Then the result really are going to be the same, exactly the same. Not exactly because some standard error affecting, but the difference that I can observe with neural network is not going to produce in linear regression. Okay, this was an example of neural network. I want to explain a lot of things, but I cannot because I don't have enough time. Then I was thinking that depending on the time that I have, I am going to explain one thing or another one. Let me know if you prefer. For me, it's okay. If you want, I can explain some more details on validation of the model. It's okay for you?
Yes, yes, please.
Okay. In this case, I prepared this slide that I have from this web page, Andrew Moore, that you can see. It's a typical example that I think it's really interesting to check because you can see an interesting way for present different techniques of validation. Okay, but remember, this is that I was explaining on the courses are very classical points, and there are several strong strategies from more engineering point of view, but these main ingredients you have to put in your mind. Then types of validation exist a lot of one. And the main effect that produce some problems when you want to validate a model is the overfitting. Everybody say overfitting for many times and in a lot of examples, but overfitting is really is an effect that you need to understand. And let me show how is producing this one with different techniques of cross validation. Okay. This is an easy example where you have a response and one covariate, you can see. And each point corresponds to one individual. Then we have 9 individuals. It's not too much, but enough, for example. And the response and information, and the idea is to fit response using information. No, I need to predict this one using this one. Okay. The first one, I can put a linear regression. No, this is the most easy. When I consider a linear regression, you know, you are minimizing the distance in vertical line between each point and the proposal model. This will be the linear regression. Let me to show another example of the model, quadratic regression, because someone say, okay, I'm going to consider x and x squared, 2 variables, x and x squared. Then I am going to get some improvement, you can see, but maybe I can consider one of them, this one, maybe is better, piecewise. You know, piecewise corresponds exactly to this one to fit with different linear in n dimension. When you have x p dimension in a strong data set, these lines correspond to some hyperplanes, no? But this is the idea of piecewise fitting using this structure, and you can see that the error is 0, no? Because it's perfect. And this is going to produce, this is an extreme example where you can see really this effect of overfitting, because I am sure the common sense say you that is not a good model because it's clear that you can see some noise in here. And when a person, new individual, maybe the response is, I don't know, but this is strange that exactly is in this point, no? This is the intuition, and the idea is to check how different cross-validation methods led to detect that this is a bad model, okay? Okay, then in our example, we have three models, this one, and this one. And if you want, neural network lives between here and, for instance, regression trees maybe here. This really, this is only three examples of the models in order to represent different techniques, okay, for validation. Okay, linear regression you can check, and the mean square error is this one, close to 2. And quadratic regression you can check, and is close to 1. And of course, this way is 0, no? Because you remember, is 0, this one is this distance squared plus this distance squared plus this distance squared, etc. Close to 1, close to, close to 0. You can consider internal and external that I was explaining, okay? Internal validation, you can see in the previous example that you are going to consider some modeling for training and check. Then this is the internal validation, this number that you obtain when you do the training and you check the result. And external corresponds to this data that you not observe and you are going to use in order to check the real error that you have. In external validation, that you know is the best improvement now of the validation procedure, because you consider some data to measure the error such that it's not considered for fitting, very, very important. From external validation, you can do training validation method, the typical one, or leave one out cross validation, K-fold cross validation, bootstrap methods, or training test validation, more complex one. This is the main techniques, but there exist several ones. But let me to show some example of these ones, because maybe you can understand the main idea on cross validation. Okay, training validation. The training validation, remember, is to choose some more large data set for training and a small one for test. Then in our case, an example, you can try blue points for training, do the line, then you can see, use blue points and do linear regression. And now check the error with red points, points that I am not considering for to do the line, okay? Blue points construct the model, red points construct the error. This is internal external validation. Then you can see the result with the red measures led to show really the external validation. Then you can see mean square error is 2.4. The theoretical result, remember, based on standard errors from asymptotic results in linear regression, this is according because it's close to 2. Okay, not too much points, then 2.4. Maybe for you is too much, but take into account that only 9 points. Okay. When you consider quadratic regression, you can see the result is closer than previously. Okay, the same idea. But of course, when you consider piecewise, when you consider blue points for fitting, then at the red points, for the error is increased. You remember you have 0 mean square and now you have 2.2. Okay. Then this is the internal external, and let me to show someone, leave one out cross validation, because from a statistical point of view, this is the most important one, or from theoretical point of view, you want is that you have to do, but many times you cannot do it. Let me show why you cannot do it. Yeah, and I am going to explain which is the reason, because you really have to consider if you can do it. Leave one out cross validation consists in the next. You consider all points and 1 point out. Okay, then you consider to do training with all black points and check the error with this one. It's like previously with training test, but now only 1 out. And then the idea is to repeat for each one. At the end, you have to do, in this case, 9 points. You have to do 9 models, and for each one, you have to compute the error. Then the result, the mean square error that you obtain with leave one out, this one is the best one. Because really you are checking each component of the error for each point, which is a contribution with a model. Really the model without them. Okay, then, but you can see it's too much expensive from computational point of view, because 9 is too much, but you have 100,000 points, then you need to do 100,000 models. And this is the handicap. But from theoretical point of view, this is the most correct. And this one, the result corresponds really to the livelihood results if you are obtaining it with statistical analysis. In this case, for instance, considering quadratic, you improve the mean square. And of course, with leave one out, piecewise, this one is the worst. And you can be, now it's clear, no, that leave one out cross validation is the most, the method such that has the capability of to detect really the worst methods, the worst models. Because in this case, you can see this is the worst because really are detecting the zero capabilities to fit nothing with this one. No? Okay, then exist several ones, several methods. And maybe I can explain this one, CAFOL, because it's between the first and the second. CAFOL consists to divide in CAFOLs, partition, for instance, 3 partitions. You consider red points, blue and green model, and error with a red. Then the second one, I consider the partition blue and red for fit, and the error with green. And finally, you consider red and green for fitting, and blue points for measure the error. Then the result with CAFOL is close and leave one out, and you can do it from computational point of view. Okay, is that the equilibrium? Then in general, CAFOL cross-validation is the most typical that you can use in order to check. You can see, for instance, in linear regression, you obtain close to 2, that you have to obtain. And mean square error for pieceways that the worst is close to 3, then they really detect that is the worst of them. Okay. Okay, this was an example. Of course, we can comment several one on this on cross-validation. And I am not sure if you want to talk of something or to spend some minutes and some comments or asking me something one, because really 4 hours is not too much for explaining a lot of things, but I think this is the most main ingredients that you need to know. Okay, let me know if you need all I can do for you. I was so quick.
So, question?
I was thinking I need some more minutes to finish, but no, at the end, it's okay. For me, because if I start to explain something else, it's not, I don't have time enough. But maybe if you want to ask me some questions or comments.
Question? No? No? Maybe you can pass us extra material because it was very clear. So very, very clear. So please, let's thank, one second. Isabella, so please.
No, thank you. Thank you, because it was a pleasure. I have to say that I prefer to be presential.
Yes.
I don't like to do online because
yes.
I like to do some pictures and to do some explanation.
Yeah. Maybe you can come to visit us.
Yes, I have.
During our summer, it's easier to find funding.
Yes.
So please, thank you very much for this series of lectures. And if you can send even some extra material, some extra slides, because that's okay. Very clear.
I think I am going to send you these slides. The last slides correspond to a series from some group that was working and develop some more didactic materials. Then I am going to send you everyone. I cannot explain. I was on this, for instance, something on regression tree, random forest, etc. Then I am going to send all the slides with these thematic points, and maybe it's good for you. And you, if you have some comment or you need more details.
Very clear.
Okay.
I had a much better picture about validating models. Thank you.
Thank you, Ayu.